Good morning. So first, let's go over the homework. So the question A asked you what was the effect on R resolution if you increase these different variables. So if we increase the selectivity factor, then R will also increase. If we increase H, then R will decrease. Remember, we want H to be small. If we increase the retention factor, usually resolution will increase. But remember, if we get a very long, very large retention factors, very long times, then the resolution doesn't increase much. If we increase length, resolution increases. If we increase N, resolution will increase. And for flow rate, that actually depends on the flow rate. So if we go back to this that shows us how H and flow rate are related, remember we want H to be small. So usually as we increase the flow rate, H will get bigger, which means the resolution will get smaller. The exception is if we work at very low flow rates, which we never do. Okay, so basically, the answer should be resolution decreases. Okay, then the calculations. I'll just remind you to watch significant figures. So first, number of plates, that's this formula. So you had to calculate that for each of those. And this is what you had for A, B, C, and D. And then you needed an average. And then they asked you to calculate H, which remember is just L divided by N. Remember that this number needs units. Okay, that's one of the very few numbers for chromatography that needs a unit, but H must have a unit, and usually it's in centimeters. Okay, then the next one was calculate retention factor. So that's this formula, and these are the values you get. So notice that three of them are in that, two are in that optimal range of 2 to 5, and then 6 is still pretty good. All right, then it asked you for distribution constant. That's the equilibrium constant, which we can get from this equation right here. And these are the numbers that you got for that. Then the next one was resolution. So remember, it's 2 times the difference for B and C. So that should be 0.72, which is not a good resolution. And then they say, okay, what's the selectivity factor? Okay, now this one, there are 3 ways to do this. You can do it based on times. You can do it with retention factors. You can do it with Ks. You only need to do it one way. Most of you were just copying the key from last year, so you gave me all 3, which is one of the reasons I know you just copied the key. Next one, H. Asked for what length of column do you need to get a resolution of 1.5. Remember, that comes from this big long equation, but we talked about how that can simplify to this equation. So then you can set up a ratio and solve for N, and then you take N times H to get L. Now, this is actually the wrong way to do this. There is an easier way to do that. Okay, remember, if it's proportional to the square root of N, it is also proportional to the square root of L. So it is much easier to just use this ratio, the resolution related to length. And if you do that, you'll get the same answer. Okay, so that's H. Again, you don't need to do it both ways, just one. And I suggest you do it the second way. It's easier, less likely that you'll make a mistake. All right, then it asked for the time to separate B and C. And again, that comes from this big long equation, but that can be simplified to this equation right here. Again, it's a simple ratio. Make sure you're doing it for C, not B. If we want the time to separate them, that time is the time for C to come off, not the time for B to come off. All right, so that one works out to 61 minutes. All right, and then finally, J and K was just the same thing, but for now for C and D, the resolution 5.21 and the column to reduce this resolution. Again, you can go through N, but again, it is simpler to just go through the length. So it's easier to do it this way over here. Either way, you get the correct answer. Okay, so I would say that the vast majority of you that turned in the homework simply copied the answers from last year. So right now you have no idea if you can do this or not, because you just copied stuff. So next week on the quiz, you're going to find out whether you can do this math. For the very few of you who actually did this yourself, and maybe are struggling with the math, I'll just quick show you when you set up these ratios. Remember, all you have to do is to take these and cross multiply. So we're going to bring the L over to this side of the equation and this over to this side of the equation. So you actually can set up, this is how we would solve for the square root of L. So you would just need to do this math. And then note that this is square root, so you do need to square that answer to get L. Okay, for the resolution, same thing. You know, we're going to bring the T over, cross multiply here, and bring this over here, and you wind up with T looking like this, and that's how you would do that math. Okay, but again, most of you don't know because you didn't do the math, you just copied answers. Okay, so that's the homework. I will post these answers online and in WeChat after class if you need to review any of this. All right, so we are going to have our last normal quiz next Thursday afternoon. And this one is going to be 20 points of calculations. Okay, so you do need to know how to do these calculations. And this quiz is going to be different than the other quizzes because we will have the quiz on rain, but we are going to use the Zoom monitoring. We need to make sure that you understand that because that's what we must do for the final exam. So we're going to actually do it on this quiz to make sure you're comfortable with it. For most of you, I understand this is what you did last semester, so this shouldn't be a problem for you to do this. Okay, so what that means is you need to sign on to RAIN with your computer, and you go to one of these websites to do that, and you can sign on through your WeChat group. You could also set it up to sign up through your email. If you want to go through that on your phone, you could do that. And then Zoom will be on your phone. So we will use our normal class meeting code to do that, like you do for normal class for that. Both of these you should be ready to go by 1:25, okay, because the quiz starts at 1:30. Okay, so before next week, you need to reread that document about the monitoring procedures where I explain this. You were supposed to have sent me an email telling me if you had any problems, and you all said you didn't, except one person that I've dealt with. So make sure you read that again, because if you miss something and you do something wrong or you're not ready, then you will lose quiz time. You need to make sure that you have Zoom on your phone. So you need to get that app on your phone if you don't have it. And make sure that you have the RAIN website on your computer, that you bookmark that so you can find that. This quiz, like the other ones, is open book. But again, you have limited time, so you cannot look up everything. Also, make sure that you have the equations for Chapter 9 ready, the equations that you needed today. Make sure you have those right there ready to use to do the calculations. You also, as always, will need a blank paper to write your calculations on. You need a calculator this time because your phone's going to be busy being monitoring you. So you need a calculator and then a pen to write things with. Okay, in that testing, here's the equations all together if you need them. I'm also going to send these slides to the WeChat group after class so you'll have all this information handy. Okay, so these are the equations that you might need to do the calculations for next time. Okay, so the monitoring with your phone. This is all in that document, but just to review, make sure that the angle for your camera shows your computer screen and your work area, and then you also should be in the picture. And you're gonna have to play with your phone a little bit to get that right angle. I found for mine, if I put it up on a big suitcase behind me, I could get that angle that you need to get. Make sure the camera on your phone is on and the microphone is off. And make sure that your phone is fully charged. You don't want the phone to die during the quiz or during the exam. When you sign on to Zoom, you need to make sure that your display name, you write your student number and then your name. And that document gives you instructions on how to do that. And just looking here, most of you have at least changed this to your name. But for the final, for sure, you need your student number. And you can just have those last 3 numbers and your name, okay, for your Zoom call. Also, you're going to have to use your phone probably to submit pictures. So you can do that. So that means that at some point during the test, the Zoom will be interrupted. There won't be a picture of you. And that's okay for brief times. If you disappear for 30 minutes or an hour, that's going to be a problem. Okay, so you can only take away your phone long enough to take the pictures and then send the pictures. And then you need to put the phone back. Okay, now note that only the calculation should be submitted by picture. In the last quiz, some of you were still giving me matching and you were giving me short answer by picture. You cannot do that this time because that phone needs to be monitoring you for as much as possible, okay? Okay, so those are the procedures for Zoom. And again, make sure you read that document. And all of this needs to be set up, ready to go at 1:30. All right, so when you're taking a quiz, I've had some of you tell me some interesting things after the quiz. Oh, I didn't know the time. Oh, I accidentally turned it in. I didn't know that I had blank questions. So I'm just going to review some of this. Most of you know this already, but just in case. So as you're taking a test, notice up here, it's going to tell you how much time you have left. This button right here, which looks like this in Chinese, that's the button you press to turn in the test. So, you're working over here. It's not likely you accidentally hit that button. It's way up in the corner. Notice that this clearly shows you, oh, I've done these ones that are white, I have not done. Okay, and you can move through these to see what you've done. You can also move this bar to move through the questions. Now, if you try to turn in the test before you're finished, it will actually give you a message that looks like this. And notice it's in Chinese, but it's showing you there's still 4 questions you haven't done. And then it gives you a choice. Turn it in, which is in white, or the blue button says, no, go back and keep answering the questions. So the system's going to try to help you. The blue one is go back. That's what you want to do. If you hit turn in, then you've got 4 empty questions, okay? So remember, just try to remember these 2 characters. That means turn in. Okay, so that's for turning in the test. Now, to submit the pictures, because there's going to be some calculations that you have to turn in by pictures, there's actually some different options. Now, one option is if you happen to have 2 phones, you could use one phone for the Zoom monitoring and then use the other phone to turn in the pictures. And that phone that you use for the pictures has to have WeChat or Rain. Now, I know most of you do not have 2 phones, and that's okay. So if you have one phone, again, you can take away that Zoom phone and use it to submit pictures. And a couple of ways you can do this. So you can actually go into Rain on the phone and submit them like most of you have done for your homework. You're very familiar with that. Most of you have been using your phone and you know how to get pictures into it. It's also possible to go through the computer using a QR code. And the Chinese teacher actually made a video for you to show you how to do this before. But the video in some places was a little bit hard to see. So I went through and took some screenshots just so you could clearly see this process. So there's several slides, but it's really quite simple to do this. Okay, so you're on your computer taking the test, and now you're ready to submit it. So you get your phone, you take the pictures, and notice when you're all done, you got to put the phone back to reposition it. Okay, but now you're taking pictures. So you take pictures of your problems, and then you come back to your computer here. And first, before we get into how to submit the pictures, I'll just note, if you're using your computer and you've got a taskbar here, like I always do, that might actually kind of be in your way. So if you want to get rid of the taskbar before the test starts, this may help you. To do that, you just come here to the taskbar and you right click, and then you will get a menu that looks like this. You choose taskbar setting, and then you tell it to hide the taskbar. You turn that on. And so now this will look like this. So notice there's no taskbar. Okay, so now you want to turn in your pictures. So you choose this option right here. Okay, this one is if the pictures were on your computer, which they're not. So this one is for your phone. So you click on that, and up will come a QR code. Okay, now notice here, I've got my taskbar. I can't see everything clearly. That's why we want to turn the taskbar off. All right, now take your phone in WeChat and scan the QR code. And then when you do that, your phone in WeChat will give you this message. Okay, so click on the plus. And if you don't notice there's no plus, so you just click on the keyboard, and then it will change to this. And then just click on the plus and the album. And you guys are used to doing this. Anytime you send pictures in WeChat, this is how you do it. You get your album, and then you choose the pictures you want to send. So you select them and send them. Notice you can send more than one picture. If you need 2 or 3 pictures, you can send them all at the same time. Okay, now once you get them sent, it will look like this. And notice I sent 3 different pictures. Okay, now you have to be careful at this step. Okay, your pictures are not there yet. So now you need to choose the picture you want to upload. Okay, so if I want to upload this picture, I click on that, and notice you'll get a check mark. And then you tell it, yes, upload that. And then as soon as you upload it, you will see the picture there. So sometimes you guys are telling me, I don't know if my picture uploaded. You should be able to see it clearly if it uploaded. Okay? It's obviously there. Okay, so again, once they come in, just click on it, accept, and then the picture will go into the problem. Okay, now if you should happen to get the wrong picture in, like I actually put 2 pictures in here, and I don't really want this picture. So then to get it out, you just right click and choose delete, and then it will go away. If you can't get it out, you can always just write me a note. You can still type in this box, even with a picture there, you can type. So, I could write a message, oh, please ignore the first picture. Okay, so if the picture's not what you want, you can't get it out, just write me a note and tell me, ignore that picture. Okay? All right, so that's how you can get pictures in directly from your computer. You still use your phone, but this is how you link your computer and your phone during the test. And then remember, put the phone back in the monitoring position when you're done with this. Okay, now when you're ready to turn in your exam, again, you're going to be using this blue button up here, and you're going to press on that, and you're going to get a message that looks like this, okay, this box. And notice there's no number, there's no problem saying you haven't done. You know, at this point, everything's blue. So if the message is telling you, are you sure you want to turn in the test? After you turn in the test, you can't change the answers. And again, this one is turn in. The blue one is go back and check. Okay, so the blue one will always kind of is the one to go back and check, go back and finish. The white one to turn in. So at this point, if you still had an hour and 16 minutes left of your test, you should probably go back and check it. Okay, so that's how you turn it in, is you click there. Okay, so notice this is what you get when you have things that are not finished. This is what you get when everything's done and you want to turn it in. And again, if you don't turn it in and the time is up, it will submit automatically. Okay, so that is turning them in. All right, so again, I'll just remind you for calculations, these are the instructions, same, they've been all year. You need your name and student number. You have to show me the work. That means equations and numbers. You have to show me which one's your final answer, you know, circle it. Most of you did that in the homework this week. If there's units, you need those, and watch significant figures. Okay, if you don't do any of these things, you will lose points. And then note again, all other questions should be submitted in the system, not by picture, okay? Because that phone is monitoring you. You don't have time to be taking and submitting lots of pictures. Okay, so that quiz will be next Thursday. Again, you need to be ready to go by 1:25. I will open the Zoom meeting probably 20 minutes before the test so that you can get everything set up and ready. And remember, 20 points calculations like in the homework. So make sure that you have a calculator so you can do those. I'm also today after class, I'm going to send the practice quiz again, the practice quiz 2. It's the same quiz that you took before, except there's one new calculation. So there's 2 calculations. And I'm sending this in case you want to practice. You know, you're not sure, you've never used your computer and how to link it to the phone. So if you want to practice what I just showed you, you can do that in the practice quiz. So that will be available until quiz time next week. But note, once you open it, that is on a timer. You have 1 hour to play with it. Now, there's no points for this. If you don't want to do it, that's fine. This is only if you feel like you need to practice answering some of the questions, especially the pictures. This will give you a way to practice in an actual quiz setting. Okay, but again, that's optional. You do not need to do that if you feel like you're fine with this. Okay, so that's quiz 4. All right, so we now have remaining 2 chapters. Chapter 11, which is gas chromatography, and chapter 10, which is gas chromatography, and 11, which is liquid chromatography. Now, there is also a quiz for these 2 chapters, because what you're going to find out is when you study for the finals, the quizzes are your friends. They're going to be helpful. They're going to help you know what's the most important things to study. So there will be a quiz 5, and I'm actually going to send this quiz to you in WeChat after class today. Now, the way this quiz works is different. After we finish the lecture for these 2 chapters, then you will take this quiz, okay? And it will be in RAIN, but you already have the quiz. So you can right now start figuring out all the answers. So everyone should get a perfect score on this quiz if you're doing what you should, because you'll have the questions today, all right? But do notice it'll be in rain, which means the order of the questions will be different. The order of the answers will be different. But the questions and the choices will be the same as what I'm going to send you today. Okay, so this quiz, though I'm not going to count as a quiz, I will count it as a homework assignment, but it's a big assignment, 30 points. So hopefully this will help most of you. Many of you have lost some points on your homework, and so if you do well on this quiz will help your homework grade for that. Okay, all right. Are there any questions on anything I've just said? Okay, all right, and again, I will post these slides in the WeChat group after class as well. All right, so I mentioned that many of you missed some points on your homework and that this last quiz will help you with that. Many of you have also missed attendance. You either haven't signed in class when I've asked you, or you've not sent me an email. So I'm going to give you a chance today to make up an attendance if you've missed it. So if you're watching here live, if you want to send me your name and student number in the chat, I will count that as an attendance for one that's missing if you have one. If you're watching the video, then just send me an email telling me you watched the video, and I'll give you an extra attendance. Okay, so it's a way to improve your attendance grade. Okay, so one person so far, send me their name, student number. The rest of you can do it or not. It's your grade. All right, so now with the rest of the time, we'll see how far we can get in chapter 10, which is gas chromatography. So this is where the mobile phase is a gas. Now, everything we talked about in chapter 9 is going to be true for chapter 10, but we're going to focus now on the mobile phase being a gas. So in this kind of chromatography, the first thing you have to do is take your sample that's in a solvent, and you need to vaporize it. You need to turn it into a gas, and you need to get it on the head of the column. Okay, the head of the column simply means the beginning of the column. So this is the head, the beginning, and down here at the end, any idea what that is? Okay, that's called the foot. Okay, so head and foot of the column. All right, so we get my sample into a gas phase and get it at the beginning of the column. And then this gaseous sample is carried through the column by an inert gas. Okay, the gas is your mobile phase. Now, notice the gas is inert. That means it does not interact, it does not react with your sample. The gas's job is simply to carry the sample through the column. So we get a separation because your solute, your analyte, interacts with the stationary phase, okay? Not with the mobile phase. In gas chromatography, it only interacts with the stationary phase. And then we have some different ways of detecting that sample when it comes off the column. Okay, so there's two kinds of gas chromatography. There is one where the stationary phase is a solid, and this one, the separation occurs by the sample adsorbing, so kind of physically sticking on the surface, and then desorbing. And this is not widely used today. This was the first type, but it's not as good. The separations aren't as good, so this is not very common today. Okay. The second one, where the stationary phase is a liquid, so we call that GLC. And this is the one where you have a particle and then you have the stationary phase that's a liquid stuck, immobilized on that particle. And this is the one where we get the partitioning, the back and forth between the mobile phase and the stationary phase. And this is widely used today. So often we just say GC, and when we say GC, we really mean GLC. Okay. But we don't say that because this one's so uncommon that we just say GC. But remember, the stationary phase is actually a liquid. Okay, now let's look at the instrument. There's lots and lots of different instruments, lots of companies that make these instruments, and there's a wide variety of prices, but all of them have the same basic parts. Okay, just like the spectroscopy instrument we looked at, always the same parts. Okay, so notice we're going to have a supply of the gas of the mobile phase, injector, something to get the sample onto the column. We'll have a column and an oven, and then we have a detector, and then data collection, which is today almost always done by computer. Okay, so the mobile phase. Remember I said the mobile phase is a gas, and its job is to carry the sample down the column. So quite often we call it a carrier gas. Instead of saying the mobile phase, we say the carrier gas. And the three most common carrier gases, remember they need to be inert, are hydrogen, helium, and nitrogen. Okay, so you should remember these three gases: hydrogen, helium, and nitrogen. We can either get these from a cylinder or an on-site generator. So the cylinders, I'm sure you've seen in the lab, they look like this. And the on-site generator would be a box like this that would deliver the gases from this system. These are much more expensive than the cylinders, so these are much more common. Okay, now these gases have to be very pure. There cannot be any hydrocarbons or water or oxygen in those gases. Okay, now, why not? Well, these things will actually interact with your sample. And remember, the gas cannot interact with the sample. So you have to use filters and molecular sieves to make sure that you remove any kind of impurities from these gases. Okay, so the carrier gas and the solute, remember, don't interact. So the different gases do not affect K, okay, because there's no interaction in the stationary phase. But these different gases do have different viscosities. And remember, viscosity affects D, that diffusion coefficient. And they also, remember, the mobile phase velocity, the flow rate, also will affect H. Okay, so both viscosity and flow rate affect H. And so you can see the Van Dienter curves for these three gases that we said are the most common. And notice that both hydrogen and helium kind of have these very broad minimums. Okay, remember, for a good separation, we want H to be small. And because these have, this wide area where H is smaller, traditionally these two have been more commonly used. Okay, but what we'll see is actually a lot of time it's the detector that determines which gas we use. Okay, so these carrier gases, since we're dealing with a gas, we have to talk about pressure. And there are a lot of pressure units out there. Of course, the I unit for pressure is Pascal. But most people, I don't know how it is in your countries, but in America, we actually don't use this unit much. China's much better. They use the SI units more. But other countries will use lots of other pressure units. So you can see a list of common units here, the atmosphere, the PSI's common unit. So this just shows you how those different units are related. We won't be doing any calculations with pressure units, so you don't need to know these, but if you're ever wondering, how are these related? This is how. Okay, so when you have a big cylinder of gas, the pressure in that cylinder is actually quite high. It's usually about 2,000 psi or 200 to 400 atmospheres. So if you put that in your column, you will destroy your column if you put that kind of pressure through your column. So you always have this thing called a regulator, and this gauge will show you the pressure in the tank. And then there's a second gauge here that you use to control the pressure going to your column. And usually the pressure you want at the beginning of the column is 10 to 50 psi, okay, compared to 2,000 in the tank. So you got to drop that pressure a big amount. So usually typical flow rates you can see here. Notice there are two different kinds of columns. One is called packed, and the other one's called an open tubular capillary column. And we will talk about those columns more a little bit later. For now, I'll just tell you there's two different kinds of columns. Okay, now these flow rates, to control it, will usually reduce the flow rate here, but then you use another meter to actually completely control what's going to your column. So sometimes if you buy an expensive instrument, the instrument can control the flow rate. More commonly, they'll have something called like this, which is called a rotometer. And you just turn this little dial, this little ball floats, and you adjust the pressure that way. If you ever need to measure the flow rate, you can do it manually with this guy right here, which is called a bubble meter. So you put a soap solution in here, and you squeeze it, and bubbles come up. And then the gas is coming, and you just time the amount of time to go from here to here and get a flow rate that way. Okay, so we've looked at the carrier gas and the flow rater and the flow regulator. So our next job is we need to get the sample onto the column. So we'll look at the injection system next. All right, so when we take our sample, we always introduce it as a plug. So you try to introduce your sample all together in a small band at the head, the beginning of the column. And you usually use this using a micro syringe. Okay, and usually this thing that we inject into, the injector, is usually about 50 degrees hotter than the oven. So what this does is it takes your sample that's a liquid and instantly turns it into a gas. This is called flash evaporation. And notice the amount that we inject is quite small. Here are those two kinds of columns. So the capillary column, we only put maybe 1 microliter, very small amount, and actually even smaller amount actually goes to the column. Packed columns are a little bit bigger, but still we're talking about microliters. So these columns, when we're putting the sample on them, we are putting very, very small amounts. Okay, so the micro syringes look like this. If you're in China and you did the lab, you've seen these and used these. So you fill this up with your sample, and then you put it here into the injector. Okay, this is the guy that's 50 degrees hotter, so that your sample in here turns into a gas. Now, if you've done this, you know when you push that needle down, you have to push a little bit. Because there's actually this thing called a septum in there. Okay, the septum sits right here, and what you're actually doing is punching a hole through this septum. And then when you pull the needle out, that hole will close, so the gas doesn't come back out that way. Okay, so your sample gets in here, and it gets turned into a gas. This is also where the carrier gas comes in. So your sample and the carrier gas get mixed together. And then all of this gets brought up to the head of the column. Okay, so notice this injector has several jobs, okay, that are listed here. Now, there are different ways that we talk about the injection. The most common is what's called a split injection. Usually, even though this syringe holds a very small volume, usually that is still too much for the column. So usually there's a system where only a small part of what you inject actually goes to the column. The rest goes to waste. Okay, and that's called a split injection. If you actually have all the sample go to the column, that's called splitless. And then once in a while, you have a sample that when you put it in the injector and it gets heated, that you ruin the sample. It's very sensitive to heat. So it is actually possible to inject the sample directly on the column. That's called on-column injection. And then you just start heating the column directly. Okay, so some different types of sample injection. All right, now one of the big problems with the injection system is it's very hard to reproduce those small volumes. If you're just using that syringe and directly introducing things, you're going to have errors of 5 to 10%, which is a pretty big error. So there are several ways we use to try to reduce that error. Okay, this we've already seen. This is that rotary valve. And this rotary valve, you have these small loops that contain an exact volume. So you fill up the loop with an exact amount, and then the gas washes through the loop, and that will reduce your errors to, notice, 0.5 to 2%, so much better. Another way to reduce the error is to use what's called an auto injector. So this looks like this, and if you're ever in a big lab that does many, many, many samples, they will have an instrument that has an auto injector. These instruments are more expensive, but notice you can put 100 samples in this tray, and they're each sealed again with that little silicon septum in the lids, and then the instrument actually does the injection, and it's much more reproducible than you are or than I am. Two other ways to improve this problem of reproducing the injection volume. We talked about them in the last chapter. One is internal standard. The other was that area normalization. Okay, so 4 ways that we can try to improve the injection volumes. All right, for the columns, as I mentioned, there's these 2 types, one that what we call packed and one that's called open tubular or capillary. The capillary column is a smaller column, and it is much faster and more efficient for separations. The lengths of these columns vary. Packed columns tend to be around 2 meters. The capillary columns can be 50 meters or more. So these columns are very, very long and made of a variety of materials. And notice, if you've worked on GC in the lab, if you had a column that was even 2 meters long, you would need a great big instrument. So usually the columns are in coils so that they'll fit nicely in the oven. Okay, and we'll talk more about these columns in a little bit. All right, now let's talk about the oven. So this column goes into an oven, and the oven needs to very carefully, within 0.1 degrees, control the temperature. It's best for the temperature of the oven, temperature of the column, to be just a little bit above the boiling point of your solute. And you want your samples to come out in about 2 to 30 minutes. And that's a good range. Now, if you have a sample that contains lots of different boiling points, then you're going to need to use temperature programming. Okay, remember, this is where we change the temperature during the experiment so that we get everything out more quickly. Now, remember, in general, if we have a lower temperature, we're going to have a better resolution. Remember, lower temperature means things come out slower, so more time on the column, better separation. But we'll also have a longer retention time. Okay, and remember, we said what do we want for a good separation? We want good resolution, at least 1.5, short time. And remember, these two fight each other. It's a trade-off. You cannot have both always exactly what you want. All right, so here's the next couple slides to show you this principle. So notice I did a separation at 45. Isothermal means one temperature. And so notice I got 5 peaks out after 30 minutes. 5's very broad. And then I increased the temperature. And notice now 5 came out in less than 5 minutes, but my resolution is really bad. So good resolution, long times. Poor resolution, short times. Okay, so now this is where we turn to temperature programming. So here they started at 30 degrees and gradually increased the temperature. And notice after just a little bit more than 30 minutes, 9 peaks out, beautiful resolution. Okay, that's the power of the temperature programming. This slide shows the exact same thing. Again, they did isothermal at 150. Notice very poor resolution and some peaks an hour and a half to come out. Okay, now we did temperature programming. We started at 50, slowly increased to 250, and notice all of these peaks coming out. Good, beautiful resolution, 36 minutes. Okay, so temperature programming. Okay, so we've looked now at this part of this. We'll come back and look at columns. The next thing we want to look at is detectors, but we'll go ahead and stop here and take a break. So 5 minutes. Okay, let's continue now and look at the detectors for the instrument. So there are dozens of these available. We're only going to look at 4. But let's first look at what do you want in a detector for the ideal detector. So it needs to have a good sensitivity. Remember, these amounts coming off the column are small. So they need to be able to measure 10 to the minus 8 to minus 15 grams per second. We want them to have a stable background. They have to be reproducible. They should have large dynamic ranges. Remember, this is the range where the range of concentration where the calibration is linear. They have to work at temperatures from room temperature all the way up to 400 degrees. They should respond rapidly. They should not change the signal with flow rate. They have to be reliable. We don't want them breaking a lot. They need to be easy to use. We would prefer that they're non-destructive. They don't destroy your sample. And then they're either going to be selective, meaning they only respond to certain kinds of things, or they're universal, they respond to everything. Now, obviously, no detector will do all of these perfectly. Okay, but let's look at 4 of the common ones that are used. So probably the most common is what's called the flame ionization detector. And notice all these detectors have 3-letter abbreviations, FID, flame ionization detector. So as I said, this is one of the most widely used. And this is actually just a burner. It's a flame where here comes your stuff from the column. And for this detector, you're going to use hydrogen as your carrier gas. So your stuff from the column with hydrogen gas comes through here and we burn it in a flame. And when your sample is burned up, it's going to form ions. And then you actually have a potential difference between this part, the burner, and up here, the collector. So you're going to get a current that forms from the number of ions that are formed. So this detector tells you how many carbon atoms. So this just explains what I just did about how the detector works. And this detector does not respond to things that don't burn. So this detector doesn't work well for water and carbon dioxide and SO2, nitrogen oxides. It'll give you a weak signal for carbonyls, OH, NH2, and halogens. Its strong point, again, is carbon. It is very sensitive to carbon. It can measure down to 10 to the minus 13 grams per second. It also has a very large dynamic range. Notice 10 to the 7. That means the calibration curve is linear from about 10 to the minus 6 to 10 to the minus 13. That's huge. That's a very easy to use detector. It's rugged. It's not easy to damage. It is destructive. It's a flame. It burns up your sample. So that's one bad point about this detector. So this is a great detector if you want to measure organic pollutants in water. Okay? Because remember, it does not respond to the water, but it will respond to the organic molecules. Okay, so FID. The next detector is one of the first ones. It's called the thermal conductivity detector, TCD. And this one you actually have, it's quite simple. You have two wires, and over one wire you have just the carrier gas. And over the other wire, you have the carrier gas and your sample. So if there's no sample, then the signal for those two wires is the same. Okay, but if a sample comes, then the conductivity of those two wires will be quite different. And for this detector, you have to use either hydrogen or helium because those have a much larger thermal conductivity than organic molecules. So that means, you've got just the carrier gas and then carrier gas plus sample. And when there's a sample, that conductivity will be very different than if there's just the carrier gas. Nitrogen has a thermal conductivity that's very close to organic, so you don't get a good signal with nitrogen. So that's why you have to use hydrogen or helium. So the TCD is a simple, rugged, again, hard to damage detector. It has a pretty good dynamic range. It's not as big as the flame ionization detector, but still 10 to the 5th is quite good. This one will respond to both organic and inorganic. So this detector is universal. It responds to everything. So we might think, oh, this is a really good detector. It's also non-destructive. Remember, the flame ionization only responded to carbon and it destroys your sample. Okay. However, the problem is the sensitivity for this detector is much smaller than the FID. It's only 10 to the minus 8. And that means that it can't be used with capillary columns. Okay, remember I told you there's two kinds of columns, packed and capillary. And capillary columns only take a very small sample size. And so this detector is not sensitive enough. And it turns out, as we're going to see, the capillary columns are actually more commonly used today. Okay, so this detector only works with packed columns. All right, the next detector is a very important specialty detector. This is called the electron capture detector, ECD. So for this one, you have a sample like nickel 63, which is radioactive. So it emits these beta particles. And when these beta particles collide with nitrogen gas, okay, so you have these beta particles colliding with the nitrogen gas. So in this case, nitrogen gas is your carrier gas. What you get is some nitrogen ions, and you get a whole bunch of electrons. So you're now going to get this signal from the electrons. This is called a standing current. Then when your sample comes, and if your sample is something that likes electrons, it will grab some of those electrons, and so you'll actually get a decrease in signal and get a peak that way. Okay, so this is what it looks like. Here's the stuff from the column going over the beta emitter, and then some electrodes to detect this current that's flowing. Okay, so this detector works with things that will capture the electron. So what will capture electrons? Well, things that are electronegative. Anything that has halogen atoms, we know they love electrons. Peroxides, which is O2, 2 minus. Quinones, which have this kind of structure, and nitro groups, NO2. So this detector will respond to those kinds of molecules. It does not respond to hydrocarbons or hydroxides or amines, NH3. And its major application is chlorinated pesticides. Okay, so it's great at detecting those. So this detector is a very sensitive detector, but it has a very small dynamic range. Okay, only 10 to the minus 2. Remember the FID was 10 to the 7th. This one, I said minus 2, it should be 10 to the 2. So it has a low dynamic range. This is easy to use. It's a pretty reliable detector. Sometimes that beta foil gets coated and you have to clean it off. And this is a very selective detector. So it only will measure molecules that like electrons. All right. And it's mostly non-destructive as well. Okay, and then the last detector is something called the flame photometric detector, FPD. This is quite often used to detect compounds that contain phosphorus or sulfur. So here, notice again, we're going to have a hydrogen air flame. So again, we're destroying our sample, and we'll use hydrogen as a carrier gas. And when these things go through the flame, they actually form new compounds. And these compounds are actually going to be excited. Okay, so the flame is exciting these and making this HPO and S2. And then we know once these guys are in excited states that they will come back to the ground state and emit light. So the HPO emits light at 510 and 526, the S2 at 394. So you use a filter to measure the light that's being emitted at different wavelengths. Okay, and then there are a lot of other compounds too that can get excited in the flame and emit light. So this detector is used for lots of different pollutants and pesticides and products from processing coal. So again, a very selective detector. It responds to certain things, but not everything. Okay, so that's 4 types of detectors. Now, all 4 of these detectors, they do not give you structural information. You know, for all of these, you get a retention time. They don't tell you about what is it. They don't tell you about the structure of something. There are some detectors that can give you more information. There's a detector that uses atomic emission that can actually identify. So it gives you qualitative and quantitative information. Also, you can use something called mass spec or FTIR to get structural information. We're not going to talk about these because we haven't talked about these methods, but just so you know, there are lots of other detectors out there. Okay, so we've kind of looked in general at all of these different components. We now want to go back and look at the column a little bit more closely. So as I said, 2 kinds of these columns, packed and open capillary or open tubular. So for packed, you have the stationary phase that's coated directly on a solid support. And these columns are best if you have a large scale separation, so big sample size. But these are also slower and less efficient separations. Okay, the capillary or open tubular, there are 2 kinds of column. There is one where you put the stationary phase on the wall of a column, and then another where you put the stationary phase on a support that goes on the wall. And these columns are really fast and efficient, but they can only handle very small sample sizes. All right, so let me show you a couple pictures that will help you understand the difference between these. So remember packed, we have this support and then this white film, that's your stationary phase. So this is what a packed column would look like. All right, and then we have the support coated open tubular. So here you put a support on the column wall, And then this R group, that's the stationary phase. And in the wall coated, this is where I put the stationary phase directly on the wall. And notice that this wall is a fused silica. Sometimes you'll see this called a fused silica open tubular for that. The difference between these three columns. A couple other pictures to, again, help you understand. So the packed, you have this solid support and then a thin film of stationary phase. And you can see the sizes here. Okay, the wall, we just put the stationary phase directly on the wall, okay, like we see here. And notice that those are pretty thin film coatings of stationary phase. And then the support coated, that's one where we put down a support and then put the stationary phase. So you can see here the white here would be the support, and then the gray is the stationary phase. And you can see these are very small particles that they use for support. Okay, so that's kind of the three different types of columns. Okay, so the packed columns can be made of a lot of different materials. They're normally only about 2 to 3 meters long, and their inner diameters, okay, 2 to 4 millimeters, so pretty small. Now, what are these? You know, we've said there's this stationary phase here on a solid support. So usually the solid supports are made of this thing called diatomaceous earth, which is basically SiO2. Okay, so these are actually the skeletons of ancient plants, and you can see a picture of what these supports look like. And they have very large surface areas. And again, these are pretty inefficient. So we put our stationary phase on top of this and then do the separation. Okay, now, packed columns are not used as commonly today. They're still used some, but they're less common than the capillary columns. Now, if you remember when we were talking about how do we make a good separation, and we talked about different things that we want to keep the peaks from getting too broad. One of the things we said is we want the particle sizes to be small. Okay, and the particle sizes we're talking about is the size of this particle right here. And remember, a smaller particle means a better separation. So you can see here that as the particle sizes get smaller, notice H gets smaller. Remember, we want H to be small. But also, if the particles, as the particles get small, that means the pressure gets higher too, and it will take a longer separation. So kind of the optimal particle size is in this range, 150 to 250 micrometers. That's kind of where we get the best particles. If you get smaller, it doesn't work well. Okay, so that was packed columns. Now, more common, the most common kind of columns today are these capillary columns or open tubular. And as we said, there's the wall coated where the stationary phase is right on the wall, and then the support coated where you have a support and then the stationary phase. So most of these, the columns are actually made of fused silica. Now these columns are much longer, often 10 to 30 meters. Okay, remember packed, 2 to 3. Sometimes these capillary columns can go up to 100 meters. Not usually much longer than that, but so these columns are much longer. And notice also their inner diameter is much smaller. This was the packed, 2 to 4 millimeters. We actually know what that is. 260 micrometers, that's 0.2 millimeters. So these are much smaller columns. The stationary phases are the same as packed, but much longer and much smaller columns. Okay, these have low capacities, so only small sample sizes, but they're also more efficient. They give you better separations, really long columns. There's a newer kind of column. One problem with the capillary is that the amount of sample that you can put on is really very, very small. And sometimes you want to use a bigger sample size. So there's a column called a megabore. These are ones, and notice they're still small compared to PAC, but they're much bigger than these. They have bigger diameters. And the reason we use these is they have a higher capacity. We can put more stuff on them for the separation. Okay, this just shows you two separations. One was done on PAC, one was done on the open tubular, the capillary. Notice they give you the same separation, same retention times. The only difference, notice this one, we used 1 milliliter of sample, this one 4 microliters. Okay. Bigger sample sizes, smaller sample sizes. And remember, this is the one that is more commonly used today. Okay, now let's talk about a little bit more about what are these supports or the walls, okay, not the stationary phase. What are these walls or supports made out of? And when they were first doing chromatography, they tried using this silanol, but what they found is that polar molecules love the stationary phase. In fact, they love the stationary phase so much that often they won't come off of it. Or if they do come off, they come off kind of slowly. So you get really broad peaks, you get tailing. Sometimes you lose your sample entirely because it won't come off of this because the molecules love the stationary phase so much. So they then started doing some chemistry. They took this guy, which is dimethylchlorosilane, and reacted it. Notice the HCl here can react. And they got this molecule. Now, this would still be a bad stationary phase because you've got chlorine, which is quite reactive. So that's not good either. So then what they do is take that and react it with methanol. Okay, so then again, the Cl can react with the H and you wind up with this OCH molecule on there. Okay, this is called a siloxane. You then have to wash it to get off any other impurities. Now, this actually makes a great support. The polar groups won't stay on this. You don't lose them. Okay, so when we talk about, we've got these particles and then a film on it. So this is the support or the wall of the column. This is what they're made of. Now, on top of that, we have to put the stationary phase. And these are the liquid coating that are going to go onto this siloxane. Now, the stationary phase, we want it to be chemically inert. Okay, we don't want it to react. We want it to interact, but not react. It has to have low volatility. Remember, we're putting this in an oven. We don't want it to turn into a gas and leave. So it has to be stable at high temperatures. It has to have a low volatility. It has to give me good separation, good retention factor, good selectivity. And there are lots of different stationary phases, but only about 10 are common. So what they do is they take these stationary phases and they're going to now coat that stationary phase on the wall or on the support. And all the stationary phases are actually based on this same siloxane we just looked at, or on this guy, polyethylene glycol. So what they do is they change the R group to make different kinds of stationary phases. And one of the big things they look at is controlling the polarity of the stationary phase. So if we make these R groups all methyl groups, then that's a very non-polar stationary phase. We can make some of these R's phenyl groups, and that's fairly non-polar. We can make some of the R's this CN group or the CF3, and these are more polar. If we make the stationary phase this, then that's a very polar stationary phase. Okay, so we have different stationary phases, and notice this is the one with methyl. Here's one where we have 5% phenyl groups. Here's one where we have 50% of the trifluoropropyl, so 50% of the R's have been replaced with this. And notice that these different kinds of columns are used to separate different kind of molecules. Okay, now, how do we know what kind of stationary phase I want? I want to do a separation. And there's lots of these different stationary phases. So how do I know what to choose? Well, the general principle for choosing a stationary phase is one of the first principles you probably learned in chemistry, way back whenever you first had chemistry. And that is the principle that like dissolves like. So you want to choose your stationary phase so that the polarity of the stationary phase matches the analyte. Okay, now, if you choose your mobile phase to match the analyte, then the analyte loves the mobile phase and it will not go into the stationary phase and you won't get a separation. So you want your analyte to like the stationary phase. So if you are separating non-polar analytes, then you choose a non-polar stationary phase. And those non-polar analytes will be the ones that come out last. Okay, they're more strongly retained. If you have polar analytes, then a polar stationary phase would be better. And the polar analytes will be the ones that will come out last. Okay, now that's the theory, but ultimately you actually have to go into the lab to determine how things are going to work, how the separation will go. Okay, so this next slide shows you a mixture of these 10 compounds that were separated on a non-polar stationary phase and on a polar stationary phase. And I just said that one of the factors you have to consider for separation is polarity. Okay, and notice for this polar stationary phase, we said, okay, if it's a polar stationary phase, that means the polar compounds should come out first or last. They should come out last. So notice the polar compounds here. We have pentanol, that's a 5-carbon alcohol, and butanol, a 4-carbon alcohol, and number 3, propanol, 3-carbon alcohol. Those are all very polar, and notice they came out last. Okay, but now let's go over here to the non-polar stationary phase. So non-polar means non-polar things should come out last. So let's look. What comes out last? 10, octane, very non-polar. 8, heptane, very non-polar. But also out here, 9, pentanol. Pentanol is very polar, yet here it is coming out late. Okay, well, polarity is one factor. There is another factor that also greatly affects the separation. Any idea what it might be? Well, it's actually right here in this table, the boiling point. Remember, if something has a low boiling point, it gets through the column faster. High boiling point takes longer. So notice that pentanol here has a very high boiling point, so it comes out later. So to fully analyze this, you actually have to look at both polarity and boiling point. Okay, but again, ultimately, you can make a theory, but you have to just go into the lab and determine it to see the actual order. Okay, now these stationary phases, we said we're putting them on the wall or on a support. One of the things that we have to do is we have to bond and cross-link the stationary phase. So we've got my support, so we actually chemically bond this stationary phase to the support, and then we also cross-link. We make reactions between the chains of stationary phase. Okay, so this forces these things to stay on the column. So it makes the stationary phase more stable. It prevents something called bleeding. And now bleeding, you probably know that word. If you cut yourself, you're going to bleed. Well, in chromatography, bleeding means you lose some of the stationary phase. In the early days of chromatography, they did not bond the stationary phase. They just adsorbed them on the surface. So then along comes a molecule that really likes the stationary phase, so it just grabs the stationary phase and carries it off the column. Or if you need to wash your column to clean it, you use a solvent, some of the stationary phase would come off. Okay, that's called bleeding, and that ruins a column. So in order to make that stationary phase stay on the column, we bond it and cross-link. Okay, so it will prevent this bleeding. And that gives you much more reproducible results. And then if you need to wash the stationary phase, sometimes something gets stuck on your column. It doesn't want to come off, so you might have to use a solvent to wash it. Then you can wash it off and keep the stationary phase on the column. Okay, the process to do this is actually what we say is proprietary. This means it's a secret. So the companies that want to sell you a column will not tell you how they do it, because they want you to buy their column, not make your own column. Okay, let's go back also and look at this idea of film thicknesses. Remember we talked about, for a good separation to keep the zone broadening small, we want those support particles to be small. And then we said we want the thickness of this film to also be small. So in a commercial column, those thicknesses are actually usually somewhere between 0.1 to 5 micrometers. Okay, remember that film thickness, it affects the retention and zone broadening. Thicker films are better if you have a more volatile analyte. Okay, thicker films mean things are going to be retained longer. So if you have something that's coming off the column too quickly, a thicker film will make it stay on the column longer. We also know that thicker films can accommodate a bigger sample size. The more film thickness, the more sample you can put on a column. Okay, but a thicker film does cause more zone broadening. That megabore column that I mentioned, and remember the purpose of the megabore column is to be able to use a bigger sample size. They typically will have film thicknesses of 1 to 1.5 micrometers. The most common for the other columns, 0.26. Okay, so pretty thin coatings. All right, so finally, we just need to look at the applications for GC. And again, we're talking about the liquid stationary phases. So GC has two major functions. The first is to separate volatile species. Okay, volatile means things that I can get into the gas phase. So we can use this to separate organic, inorganic, metal-organic, biochemical species that are volatile. It's a way to purify them. The second way that we use this is to help us identify unknowns. Quite often we have mixtures of things. So we will use GC to purify it, and then we can use other methods to do the qualitative analysis. What is this? And the quantitative analysis. Now, remember, GC alone, the only thing it gives me is a retention time. Okay, remember, I get that chromatogram, and all I get is that TR. And that really does not identify something. There might be lots of things that come off at that time. But if I take that peak now and I collect it, and now I go do other chemistry on it, methods we haven't studied, but something called mass spec and IR, these are very good at answering the question, what is it? Okay, so we use GC to purify it, and then I go do more tests using other methods to tell me what is this thing that I don't know. Okay, so for qualitative analysis, one of the things you can do is you can actually use it to determine if something is pure or not. So if you have a sample and it's supposed to be pure something, and you do a quick GC and you get 2 peaks, then you know it's not pure. Or if you have a sample and you know that your peak should come out here, and it comes out here, then you know that's not the right thing. Okay, so the extra peaks can tell you there's impurity, and the size, the area of the peak tells you, how much of the impurity is there. If you have a system that you have studied, it's something that you're pretty sure what it is, and you know this is where it should come out, and it comes out, oh, sorry, it's supposed to come out here, and that's where it comes out, then that can kind of confirm that that's what it is. But you do have to remember there's lots of things that might come out at that time. And sometimes if your conditions have changed, the time can change. So as a qualitative technique by itself, it's not very useful. Okay, quantitative, again, we can use the signal and we use the peak height or peak area. Peak area, much better, much more common to answer the question, how much is there? Okay, and you can get pretty good errors, about 1% if you're careful. Okay, so that is GC. Okay, so next week, remember we have a quiz. Next Thursday, you're going to be using Rain and Zoom, so you should be studying for the quiz, and then make sure you prepare. Be ready to take it, using both Rain and Zoom. Friday, we'll have our normal lecture. We finished 10. I wasn't sure, but we did. So we'll be looking at chapter 11 on Friday. Today, I will be sending several handouts in the WeChat group. So I will be sending, and also they'll be on Baidu and in Dropbox as well. So I'll be sending the answers for the homework that was due today for chapter 9. I'll be resending the procedures for the final exam and the quiz, using Zoom and Rain. So you need to read this, make sure you understand it. I will send the slides from the early part of the lecture today, showing some screenshots from Rain. I will send the practice quiz in Rain. If you want to practice sending pictures. Remember, that is optional. You can do it or not. Your choice. And then I will be sending quiz 5. So after today's class, you should be able to answer some of those questions in quiz 5. And remember, later, I will ask you to do this quiz in Rain. Okay? Any questions?
Yes. Lasha, I have a question.
Yep.
For these past homeworks, was the deadline before class like 8:30 or maybe prior to that?
For what?
The homeworks you're giving, like
the deadline is always 8:30.
Before the class starts, right?
Yep.
Okay. I just wanted to confirm that.
Okay. Anything else?